find a matrix P, puts the following 4 by 4 matrix A in Jordan canonical form. Now, when do we use Jordan canonical form? If we try to put A in diagonal form, two things can go wrong. First, the eigenvalues for A might not be in our field of interest. Then, even if they are, it could turn out there's not a basis of eigenvectors. So, for our A here, the eigenvalues are all going to be equal to 2, which is good, but we won't have a basis of eigenvectors, which is bad. So we'll need to go to Jordan canonical form instead. Now, how do we set that up? Well, Jordan canonical form is going to be block diagonal. The blocks are going to be Jordan blocks, which means there's 0 everywhere, except on the main diagonal, we have our eigenvalue. On the diagonal above the main diagonal, we have 1s. Now with that, we need to get a handle on what kind of blocks can appear. So we'll use the minimal polynomial to get the size of the largest block for a given eigenvalue. Then, if we find the dimension of the eigenspaces for a given eigenvalue, that'll tell us the number of blocks for that eigenvalue. So, let's take a look at eigenvalues and eigenvectors. So, we set up our characteristic polynomial. When we work that out, we're going to get lambda minus 2 to the 4th power. So we only have one eigenvalue, which is 2 with multiplicity 4. To get the eigenvectors, we set up the null space of the matrix A minus 2i. So that's going to give me this matrix here. So this null space is going to have as a basis 0, 1, 0, 0, and 0, 0, 0, 1. So we'll call these V1 and V3. Of course, we check our work. So it should work out that A times V1 is 2V1. A times V3 is 2V3. With that, we note we're going to need 2 Jordan blocks for this Jordan canonical form. So there's no basis of eigenvectors here. Let's look at our minimal polynomial. So if we take A minus 2i, it's equal to this matrix, which is not equal to 0. If we square it, we do get 0. So our minimal polynomial is lambda minus 2 squared. Checking our work, lambda minus 2 squared divides lambda minus 2 to the 4th power. That's our characteristic polynomial. This means we're going to have the largest Jordan block as a 2 by 2 matrix with eigenvalue 2. So since I only have 2 blocks, that means they both have to be 2 by 2. So our Jordan form is going to look like this. Now, if we want to get our matrix P, I have to figure out how to get the other 2 basis vectors. So if we interpret what this matrix says, it's saying we're going to take V1 to twice V1. We're going to take V2 to twice V2 plus V1. That's what that column says. We're going to take V3 to twice V3. Then we're going to take V4 to twice V4 plus V3. Now, we're going to set up the second and fourth equation. So for the second equation, I'm going to have AV2 equals 2V2 plus V1. Move the 2V2 to the other side. That's just going to give us the matrix we were working with before. So I want to solve this. Then when I do that, we're going to wind up having that Z is 1, X is 0, Y and W can be anything. So we'll let them be equal to 0. And so I get that V2 is equal to 0, 0, 1, 0. Same idea. We're going to have AV4 equals 2V4 plus V3. We move the 2V4 to the other side. That's our matrix from before. We multiply, and then we get X equal to 1, Z equal to 0, Y and W can be anything. So we let them be equal to 0. So that gives me my V4 equal to 1, 0, 0, 0. So now we have 4 basis vectors. Let's see what happens when we conjugate. Set up our basis matrix P. Take V1 through V4, load them in as the columns. We're going to need P inverse. So I note P times P transpose is the identity matrix. That means P is orthogonal. So its inverse is just equal to its transpose. Now, we conjugate. So we have P inverse AP. We're going to have P on the right-hand side, since that's the matrix that has the eigenvectors in columns 1 and 3. We work everything out, and then you note our Jordan Canonical Form comes out in the final step. So we have our eigenvalues equal to 2, and we have two 2 by 2 blocks.